In this class, we will see in detail about the semi-classical treatment. Particularly, we are going to see the matter and radiation interaction. That is, particle interaction between the particle and the electromagnetic wave. And in particular, we are going to see about the emission process and absorption process. First, we will see what is meant by semi-classical treatment, uh, in which the radiation field is treated as classical field. That is, the electromagnetic fields are treated as a classical field, and the interaction between the particle and the radiation field then correspond to a certain interaction term in Hamiltonian, which are treated by time-dependent perturbation theory. So, hence we are calling this as a semi-classical treatment. The particle, including the Coulomb interaction between them, are treated quantum mechanically. That is the why this is called semi-classical radiation theory. Consider the Schrodinger equation, that is I h cross delta psi over delta t is equal to minus h cross squared over 2m del squared psi plus v psi. This is a normal condition. Then in presence of, that is without presence of electromagnetic field. Now, in presence of electromagnetic field, the Hamiltonian can be written as H is equal to P minus E over C A whole squared plus V plus E pi, where A is the vector potential and pi is the scalar potential, which is related to the electromagnetic field. Now we will expand this and we will find the solution. So, in presence of electromagnetic field, Hamiltonian is equal to, as I said, it is 1 over 2mp minus E over C A whole square plus V plus E times the pi. So, since P and A do not commute, the Schrodinger equation in presence of external electromagnetic field thus take the form that the first term you expand, you will get a minus p whole square, that is a squared, that is p squared over 2m plus e squared over c squared 2m, because 2m is a common. So then this will become a squared minus E over 2mc P dot A, because P and A will not commute, so you cannot write this as 2 times P dot A. So here you have P dot A and A dot P. Of course, remaining terms are the same. That is V and V and E pi. So. Now we got this expression. Since the electromagnetic fields are weak compared to the potential, then we can ignore the second term, because A is small, then A squared will be very small, so you can ignore the second term and you keep all other term. That is, and also replace P by its operator. Here this P is I h cross del. So I h cross del, if you square it, you will get minus h cross square del square. Then here the third term will become minus I h cross. Minus of minus will become plus, plus I h cross del dot A. Similarly, the third term A, this P comes after A. So this will be as usual I h cross minus I h cross, minus of minus will become plus. So naturally plus I h cross A dot L. The other two terms we are keeping as it is, V plus E pi. So which is equal to I h cross uh, delta psi over delta t. So we got this expression, and assuming that the weak electromagnetic field, that is E times pi is very much less than the potential V, then we can cancel this. And also from Coulomb gauge, we know that the divergence of A is equal to 0. Now, keeping this in mind, that is a divergence of A equal to 0, we will simplify this one. You bring this pi inside the bracket. So, first term will become del squared psi, second term will become uh, divergence a dot del a dot a psi, and the third term this a dot del psi. Fourth term v psi as it is. You will get it. Now you expand the third term. Sorry, you expand the second one. Second term. If you expand this, first you take the derivative with respect to psi, you take a. So a dot del psi you will get. Then you keep psi as it is, then differentiate this a. So that divergence a, you will get divergence a. Uh, then all other terms remain the same. Here, from Coulomb gauge, this term, third term will be equal to 0. So remaining term we will get, we will simplify further this one. So now we got this expression. Uh, you see the second and the third term. You just add both up term, then you will get IH cross EMC. That is, you are adding both the term, then you will get this one. Here I brought this to third place, third term, IH cross E over MC, A dot del. Then you bring this to second term. Now, first two term is unperturbed Hamiltonian. This is the perturbed Hamiltonian. See, we have assumed that the electromagnetic field is weak comparing this potential V. So, this electromagnetic field we are taking as perturbation. So, this is related to vector potential is related to electromagnetic field. So it is the perturbation, amount of perturbation. That is H prime is equal to I E H cross over MC A dot del. So A is, A is equal to A, which is a function of R and T, is equal to A naught e power I k r minus omega t plus A naught star e power minus I k r minus omega t. Now we will proceed further using this. So the perturbed Hamiltonian H prime is equal to I e H cross over MC dot del. So now you, as I said, you apply the first order time dependent perturbation theory. I have mentioned this in starting up my class. So uh, to apply the first order time dependent perturbation theory, you take the inner product with the H prime. That is pra k H prime get n, which is equal to I H cross over MC K, because I am writing this left hand side, I am taking this, and right hand side I have this one dot del. So this A is replaced by this one, that is A naught e power I k r minus omega t plus A naught star uh, e power minus I k r minus omega t. So this is equal to A. So I am replacing it. Now you take the time factor outside, that is in the you can separate this into two part, that is and also you take this time dependent factor outside. So first term will be e power minus I omega t, and the same thing will come I e power I e h cross over mc. This a not I am taking out. So this is the uh, taking the inner product k e power I k r dot del uh, get n. Similarly, the next one I am taking minus of minus omega t I omega t will become plus I omega t, and the rest of the term I am keeping as it is. So I have separated this into two portions. Uh, just now we got this expression. According to first order time dependent perturbation, the probability amplitude, that is a k, which is a function of t, a k one indicate first order perturbation, which is equal to 1 over I h cross integral 0 to tau e power I omega k n t uh, k, that is pra k h prime get n dt. This is we are integrating over the time. Here the perturbed Hamiltonian depends on time. So now what you are going to do is you apply this expression here. That is blue color bond I have given. This is inner product. This is in the left hand side. You take this right hand side. So if you apply the right hand side here, then you will get e power I omega k n t. Then this one will come. See, in both term, first term and second term contain I e h cross over mc. I e h cross over mc. So I am taking that as a common factor. Then a remaining thing, here you have e power minus I omega t a naught, this inner product, plus here also, because omega kn is common for both terms. So plus e power plus e power I omega t. Here you remember this is e power I omega t. Already I have taken this out. I e h cross over mc. So here you have a0 star and this inner product k e power minus ikr dot del uh, get n, so we are integrating over dt. Here, if you multiply this and this, you will get e power I omega kn minus omega t. This one. So a naught you keep as it is. This inner product also you are keeping as it is. Then the next term you will get e power I omega t. Here e power I omega kn. Here plus omega. So this will become e power I omega. If you multiply this and this, you will get e power I omega kn plus omega t, and this inner product integrated over time. Now, outside the integral, you have I h cross. Here also, I h cross contain both in the numerator and denominator, which will get cancelled. This I will get cancelled with I, h cross will get cancelled with h cross. So you will get e power mc in both the term as a common, e power mc. So I am taking that e power mc in both term. Now we will reduce it further. So now we got this expression. Uh, you can, if you analyze carefully, in the first term, this inner product is time independent. So I am taking out. Already I have taken a not outside, as it does not depends on time. Similarly, the second term I am taking inner product outside, as well as a naught 0 already I have taken. So now if you integrate this first term, you will get e power omega kn minus omega t over I. This I brought here. Omega kn minus omega. If you apply the limit, upper limit tau, then t will become tau. If you apply lower limit t, then e power 0 is 1. So this will become minus 1. Same is the case here. Here also this I brought here. So we got this expression. For first term to be dominant, you can see this. Omega kn must be equal to omega. That is, H cross omega kn is equal to H cross omega. This H cross omega kn is nothing but 4 omega kn is nothing but 4 angular frequency. So this will be equal to ek minus en, which is equal to H cross omega. So from this, we can understand Ek is equal to En plus H cross omega. If we bring this En to right hand side, that means the final energy is equal to initial energy plus H cross omega. So the energy is increased by an amount H cross omega. So this is upward motion. Then second term, if second term is dominant, then that means H cross omega kn must be minus H cross omega. That is, omega kn must be minus omega. So which represents that Ek minus En is equal to minus H cross omega. That means Ek, if you bring this En to the right hand side, this will become En minus H cross omega. That is, final energy is reduced by an amount H cross omega. This is the downward motion. First, we will take the upward motion one. So this is the expression we obtained finally. Now take the first term to be dominant. Then the probability, that is probability density for the particle moving from nth state to kth state, which is function of time, is equal to the square modulus square of this probability amplitude. Here, if you are taking modulus square, then I you can ignore I. So this will become E squared mc squared because we are taking only the first term. E squared over m squared c squared, then modulus a naught squared, then this inner product modulus of this inner product square. Then if you square this exponential term, you will get 4 times sine squared omega kn minus omega tau over 2 omega kn minus omega square. So here the 4 sine squared, that is, I have already explained this in the harmonic perturbation. If you square e power I theta minus 1 whole, if you square e power I theta minus 1, then you will get uh, sine squared theta by 2, 4 times 4 sine squared theta by 2. I have used that fact. So you can refer my earlier lecture on harmonic perturbation. So you will get this. When you square the exponential term, you will get 4 times sine squared omega kn minus omega tau over 2 omega kn minus omega whole square. And now I will come to this factor, that is A naught squared. If the intensity of electromagnetic wave in a small frequency range delta omega is I omega delta omega, then we can write that is take the average of the Poynting vector over the period of oscillation. Then modulus A naught squared is equal to 2 pi c over omega squared I omega delta omega. So you keep this in your mind, then we will simplify this one. So now you can simplify this. I have written a naught square as shown in the red color bond. That is 2 pi c over omega squared I omega delta omega. Here you can see I can cancel c squared with this c. This will become simply c. Uh, then you can take this 2 and here there is 4. If you multiply both, you will get 8. That's what I have written here. So this will become 8 pi. Here you have 1 pi e squared over omega squared m squared c, not c squared c. And the remaining term I am keeping as it is. Uh, Now consider the absorption process. That is, your particle is absorbing some energy. Then your EM radiation, assume your EM radiation is not monochromatic, has a frequency range. Then you will add this. That is sum over all the frequencies, summation over omega. Then all you keep all other thing as it is. You will get like this. So we got this expression finally. Then here I like to highlight few important points. This is when the frequency is a discrete one. Uh, Remember that here your spectrum is peaked at omega kn. No doubt about it. When omega is equal to omega kn or omega kn is equal to omega, you will get maximum peak. Peak is very high at omega kn is equal to omega. And also you further assume that the variation in the frequency is infinitesimally small. That means the summation will become integration. Here, only term that depends on time is this sinusoidal and this omega. So you divide, that is probability density per unit time. That is 1 over tau. Uh, Modulus AK1 whole squared is equal to this one. Because tau I have introduced here. I am going to the summation. I am going to change it into integration, which tends to minus infinite to plus infinite. Now, if you carry out the integration, then the integral minus infinite, this term will become sorry, this if you integrate this is a standard integration, you will get pi by 2. So if you replace the entire integral pi by 2, this 8 pi will become pi squared, and here there is 2 here, so this 8 will become 4. So finally you will reach with this expression. Similarly, for downward transition, that is since it's a downward transition, in order to differentiate instead of k, I used k prime. So your this is after all notation. Just changing notation, your physics will not change. So I have so similar manner I can arrive this expression. Only thing is except here exponential is plus, here exponential is minus. Remember that you are taking modulus squared. In both cases, probability square of the that is probability square of the probability amplitude, that is probability density, is same if you compare this compare this expression and this expression. The probability is same because all are constant, and this is modulus squared I omega k, and everything is you are taking the modulus square. Naturally the sign does not matter, so both this and this upward transition and downward transition, the probability of upward transition and downward transition both are equal. That means we can conclude that both the upward and downward transition have same probability. That is one of the very important point. Thank you very much for watching my video and supporting me continuously. Thank you very much.